So let's break this into, remember, we have our, for related rates problems, we've got our 4-step process, right? And it's good to break this down into steps, I believe. Step 1 is what?
Define all the snapshot.
Yeah, good. So we remember that we want to model this. Imagine that this is one frame in a movie, right? This is a film, and so we're looking at something that is dynamic and changing. But the information that's given and asked about here refers to one snapshot in the otherwise changing movie, right? Okay, so just one frame of the movie. So step 1 is we need to define what our variables are and write down what we're known and what we're trying to find. And we might add to that list as the problem goes on, right? That also includes potentially a picture, right? Because a lot of times it really is a good idea to have a picture to kind of remind and sometimes it's essential to remind us how these quantities are related. And some of the examples we've dealt with already, remember, the relationship that we've come up with for our parent equation has been a geometric relationship. And so we've needed that picture to be able to build that relationship, right? So this one's a pretty simple picture, right? This is all review what we did last time, right? We just said we'll take a cross section of the pile. And as I recall, we said that we were going to call this distance, the radius of the pile we'd call x, and the height of the pile we'd call y, right? And so what information were we given?
We done.
That x
Okay,
equals
good. So
3y over 2.
Good. Yeah, so we knew that sand is being added to the pile at a rate of 10 cubic feet per minute, right? And so that's got to be, you just look at the units. Cubic feet per minute, those are units of volume per time, right? Volume over time. And so that has to be V dot, the rate of change with respect to time of volume. So that was positive 10. And we don't, as long as we're consistent with the units, we don't even have to include the units because it makes it look messy, right? So there's 1.
Y equals 10, 12, 15.
Y equals 15. Okay, there we go. So y equals 15 in our units, right? And then what were we asked to find? Y dot, right?
Y dot.
Y dot. At what rate is the height of the pile changing? So the rate at which the height of the pile is changing with respect to time is what's implied there, right? So then we're looking for Y dot. So there's step 1. Okay, what was step 2?
The Y.
Parent equation.
Yeah, right. So now, and I want to really reinforce this, because a lot of times people get real panicked when they have to come up with an equation here. But remember, the parent equation is going to be a static equation. We're going to ignore all the dots and see if we can just come up with a relationship that between all of the variables without dots. And so this is just a geometric formula, right? That's all this is. We've just got, for step 2, we just want the formula for the volume of a right circular cone. So volume is just 1/3 pi r squared. So for us, that's x squared y, right? Where y is the height, okay? So there it is, but what else does it tell us we've got to do? Well, it doesn't tell us we've got to do. What could we do here to simplify this greatly? And this is really an important deal. Think about this. The next step in our train is going to be to relate the rates by implicitly differentiating with respect to t.
So we want to realize that x equals 3y over 2.
Right. We want to relate the variables and make a substitution to eliminate a variable. That is huge in math. That is such a big deal. It makes math so much easier if you can eliminate variables by substitution, right? This would be kind of an ugly thing to deal with. If we just differentiated this, just powered through it and implicitly differentiated, it's going to be ugly. We're going to get v dots and x's and x dots and y's and y dots in multiple terms, right? Because we're going to have to use the product rule on the right side. Agreed? So instead, let's do a little preliminary work here, and let's try to substitute for x so we can end up with some formula up here, some equation that's gonna solve for, that's gonna be written for v in terms of y only, because look at our list. We're given a y value and asked about y prime. Nowhere are we given or asked about x. Now, we could go back and solve for x and x dot, right? Not x dot, actually. We could solve for x, but we could relate x dot to y dot. And then geometrically figure out what x is. But that's a lot of extra work, right? We'd like to avoid that. So let's use this other piece of information that we're given. It says the diameter of the pile is approximately 3 times the height. So think about that. Diameter is equal to what in terms of our variables?
3x,
Diameter
or 3y.
is, well, what's
2x.
2x, right? Diameter is 2 times the radius. So
Oh,
diameter is an
okay.
important word. What does is mean?
Equals.
Equals. So diameter, so 2x is 3y, right? And which variable do I want to solve for if I want to get rid of the x's?
X.
X. You solve for the variable you want to eliminate by substituting, right? So we get x equals 3/2 y. There's our substitution equation. And we'll just substitute, whoops, right there. Okay? And so step 2 culminates in the equation v equals, v equals pi over 3, we'll combine those constants, times the quantity 3/2 y squared, right, times y. And so what's that give us then? If I square everything in the brackets, I'm going to get what? What? 9/4
Y squared.
y squared. So if I multiply that by the constant out front, 9 over 3 is 3 on the top, right? So we're going to get 3 pi over 4. Agreed? That's what all this stuff is going to simplify to when I square it out. Times what? Y cubed, yeah. So there's our parent equation, right? We've got v as a function of y only is 3/4 pi y cubed. Okay, so now step 3. What's step 3?
That's a great question. It's to add the dots.
Now we're gonna relate the rates. We need to get the dots back in there so we can relate the rates, right? So we'll have to just, to get them there, we're just gonna implicitly differentiate with respect to time. Yeah, because our rates are rates with respect to t, right? So step 3, which is relate the rates, just means implicitly differentiate with respect to t. So what do we get? Left side, what do we get?
Yeah.
V dot. Oops. What just happened?
Oh.
Guess we can't rap today.
Oh.
Yeah,
Woo.
Yeah, I was gonna have to quit.
Oh.
Fortunately, I don't. What do we do with the constant? 0. Well, get right, but we just, when we differentiate, we'll just pull the constant out front and leave it there, right? So we get the constant, we separate the constant out front, and we just differentiate 3, or y cubed with respect to t. So what am I gonna get?
3y squared.
So I'm gonna get times 3y squared. What? Not done.
Times
Y.
y dot.
Y dot.
It's like why dot?
Okay, because I've got to use chain rule here because I actually have 2 layers, don't I? I've got the derivative of something cubed, but then I've got the derivative of what's behind with respect to t, which is not 1, right? dy dt is not 1, that's y dot. If I were differentiating with respect to y, I wouldn't have had to include anything beyond the 3y squared, right? Okay, so now that's our answer. Let's just simplify. So that gives us 9 pi over 4 times y squared y dot, right? Last step, plug and chug. Yeah, we'll just isolate the part that we're trying to find, which is that guy, right? So y dot equals what? So I'm gonna multiply by 4/9, right? So I'm gonna get 4 v dot over 9, what? Pi y squared, everybody agree? Multiply by 4 and divide by all that stuff. Multiply by the reciprocal, in other words, right? And so now I just plug in values.
Oh, it's a smart way to do that.
Okay. So I get 4, I gotta go back up to my list, wasn't that 10, v dot? Yeah, 10. And I'm gonna go ahead and include the units now, just to demonstrate something. So that's gonna be cubic feet per minute divided by 9 times pi times 15 feet squared. And what do I get? Well, I'm gonna get all of the numerical part, which is just what the 40 over 9 times pi times 15 squared, so 225 times 8 would be 1100. No, hang on. 225 times 8 would be 1,000, right?
Yep.
Yeah. Plus another
225 times
3.
8 is not 1,000.
Wait, what?
Yeah, 225 times 4 would be 1,000.
I mean,
Yeah,
two,
that's
I mean,
1800, 1800.
225
Times
times
8 is 1800.
1,800.
1800 plus
So 2025.
Plus 225.
1825, right?
So it'd be 2025.
2025.
Whoa, what? No, no,
2025.
that's not right. No, it's 2000, 2025.
2025, there we go. Yep, that's right.
You guys?
That's really worked out there.
2025. Okay, so pi on the bottom, and then what are my units going to be? Do they work out?
Feet per
I
minute.
get cubic feet per minute divided by square feet. So I get feet per minute, don't I? Right? So that's my answer. I could reduce it, but I think they probably just, did they just ask for a, what is the, does it ask for, I can't remember on the, it'll either ask for an exact answer or it's gonna ask for a rounded decimal answer. If I had to simplify this, I guess I could divide top and bottom by 5, right? And, yeah, and then I'd get something that would reduce it. No. Okay, make sense? Okay, so that was step 4. And that's it. I think another one that's usually a pretty good one to go through, which I'll do today. How about, how much time we got? I gotta really think about which one am I doing.
It's 42.
43, okay. So one is gonna be a distance on a curve. Let's do that. And let's do one where we can get a trig function in there.
No, go on.
Okay. So let's find Okay. How about that? So we wanna find the rate of change of the distance between a point moving on the curve, y equals sine x, where the x dt is positive 2. Okay. I wouldn't even have to put units there. dx dt is just going to be 2. Right? So what's step 1 going to look like? Snapshot. Okay, so let's draw the picture. Picture is just going to be a sine curve, right? So we'll just pick some arbitrary value out here, right? We don't know. A point is representative of any possible point. Doesn't matter where it is. Regardless of where it is, what are the coordinates of that point going to be? X and y, right? Okay, well, okay, we can't plug in any 2's yet. Just in general, what are the coordinates of that point? X and y we'd rather not have 2 variables there. It's gonna have to be a variable though, right? So let's write it in terms of x, how about? X, and what's gonna be the y value? Sine x, tells us, right? So whatever x is, the y value is gonna be the sine of that. We agree? Okay, so then if we're calculating a distance, this is the distance, right? So how am I going to set up maybe a relationship there? Because this is D. This is what we're looking for, right? We'll call that D.
It'd just be x squared plus sine x
I'm
squared.
going to call it capital D.
Capital D equals x squared plus sine x squared.
Yeah, right? This is just a Pythagorean identity again, right? That's just a right triangle. That coordinate, well, that's just the x coordinate.
Or the square root of x
So
squared
that's
plus
x.
sine x squared.
And that's sine x, right? So d squared equals x squared plus the square root of sine x squared, right? That's going to be our parent equation, isn't it? Right? Well, what do we know here? Is there anything we know about this? So step 1, we have to include all the stuff that we know. Well, we're getting one thing, aren't we? For our snapshot, what's the one number that we're given? 2. So what's equal to 2?
dx dt.
So that's x dot. Good. What are we trying to find?
D dot.
D dot, the rate of change of distance, right? So we're trying to find capital D dot. Okay, and so now we got to do our parent equation. Well, we basically got it here, right? It's geometric. So our parent equation, step 2, is just Pythagorean theorem. Right? X squared plus the square root of sine x squared equals what?
Wait, why wouldn't we have the square root around? Oh, yeah. What-
Okay.
Wait, what is it?
And what is the square root of sine x?
Wait, yeah, why
squared?
is sine x rooted?
Why is what?
Why is it the root of sine x?
Because, oh, never mind. Why did I make it the root of sine? Why did I do that?
Well,
I don't know. I guess I was thinking it was the square root of sine x in this problem. But it's not, it's just sine x. So it shouldn't be. So let's fix that. So then that's just gonna be a sine squared, right? Why did I do that? I think I heard you guys talking about square roots.
I said it was the square root of x squared plus
Okay,
sine
and that's
x
probably, yeah, so that's,
squared.
so I'm blaming it on there.
What I said was mathematically correct.
Oh, it is, I agree. Okay, so there's our parent equation, right? Looks good. Right, it's only got x's and d's in it. Right, so now what?
Now we can throw some dots in there.
Yeah, we gotta differentiate, good. So step 3, we're gonna relate the rates, implicitly differentiate. What's first term give us?
2x. Plus
2x
Oh, X dot.
X
Yeah,
dot
X dot.
plus
Where's Michelle?
Two sign,
Where's Michelle?
2 sine x.
X dot,
No.
no,
Sin X dot.
Yeah, because look, I've got two layers here, don't I? I've got something squared. What's the derivative of hand squared?
That, and then.
Oh, wow, it's
And
cosine.
2 hand, right?
Do hand dot.
Times
Cosine.
cosine x times
X dot.
x dot,
Damn.
okay? Right? So we actually had an extra, we had 2 layers in the first one, 3 in that one, right? And on the other side,
D dot. D dot.
2D D dot.
so I got, once again, chain rule. Derivative of hand squared is
D.
2 hand
That's a
times
double D.
x dot, right? Or, I'm sorry, d dot, not x dot. Right?
Yeah.
That look good? Okay, so then we're trying to solve for d dot, right? So all we've really got to do here, I could divide both sides by 2 though, right? That'd help. Let's divide both sides by 2. And then all I've got to do to get the d dot by itself is just divide both sides by d.
Yeah.
Right? So step 4, we get d dot equals that stuff man, you know what? I must have. Did I miss something on here?
Yeah, how would we find what? G?
Oh, no, we're
because
okay.
We can just plug
Yeah,
that
we're
in.
okay. Yeah, we're fine.
That means it's.
Sine x cosine x times x dot divided by d.
Square root of x squared plus sin x.
Yeah.
Squared. See? You need it.
Okay, so then what do we
Plug into.
get? Yeah, so now we can rewrite d. We don't have a value for d, but we have a formula for d, right? We know that based on our parent equation, d is just the square root of x squared plus sine squared x, right? Okay, and we end up with what? We end up with
2x plus 2 sin x.
2
Cosine x.
x plus 2
Sin x.
sine x cosine x divided by the square root of x squared plus sine squared x, right? Okay, so what do we find here though? We find-
D note x.
We
Well,
find,
that's just the
the
rate.
question just wants us, and think about what the question is asking.
We don't know the question.
Yeah, the question is only asking us to find the rate of change of distance between the origin and a moving point
Perfect.
if dx dt is positive 2.
So we got-
Did it give us a specific value of time? It didn't, did it? Right? In order to give us a specific x value. So that's our answer, right? But look what we got. What we've got here is now we have d dot as a function of x, right? So that's good. We got d dot of x equals that stuff, right? So that's general. Now I could plug in any value of x I want, and it's going to tell me how fast the point is moving away from the origin. If they had given me, and this would have been a different problem, but if they had given me more information on this one and said, find the rate of change of distance when x dot equals 2 units per second and x equals 10, right? Then I could have just plugged in 10 down here and gotten a numerical answer, right? Okay. Does everybody see? It's kind of a subtle point though. Do you see why that's the best I can do here? I'm not given enough information. Am I really even given a snapshot up here?
No.
Not really, because it's just telling me that x dot is 2, right? It's not telling me, it's not giving me an example of, you know, what's a static variable here? What, you know, for what value of x? At what snapshot are we finding this? It's just saying this is true. The rate of change of x is always 2 units per second. Now come up with a formula for d, right? That's going to involve that X dot.
Is that 2 units per second, is that arbitrary, or is that a specific value to that function? Or is
No,
specific-
they're saying that it's, what the math guys have told us here is that if a bead is moving along this function, it's always gonna be moving to the left at a rate of 2 units per second. So it's gonna be moving pretty fast here, isn't it? Right? Because the X component of the velocity has to always be 2. So it's gotta rip through there pretty good, but then it can slow down, because seen from above, the bead would have to just move at constant speed the whole way, right? To be moving at constant speed, where it's having when it has a large component of vertical motion, it's gotta be booking pretty fast for its X component to stay constant the whole time. That's not important to the problem, but you see how you, can you kind of conceptualize that? Okay? It's a good problem. Okay, does that make sense? Questions on that? I think probably there's only one other kind of problem I wanna go through. I'm really not gonna have time to do it today. When are we out of here?
6 minutes.
6 minutes? 1 minute. 43. What else? Okay, here's one other quick one we could do. This is cool. I love this one. Let's just say, love this problem. Evaporation, yeah. Okay. I like this because it's a simple but effective mathematical model that we can come up with for something real. So here's the problem.
Mr. Roy, do you have class seventh period?
Yes.
Do you like,
What's that?
do you like them?
Sure. Well, how do you ask?
Just curious. Very
Should
professional.
the Chromebook stuff?
Update the. It's supposed to be an A on Howard.
Did you update it?
No,
Just do
Well,
it.
it's
Your
a
one
time.
job again. Your one job in this world. Update
I
that.
know.
You guys hear about?
I think this is really cool.
You guys remember Marcus Walker? Yeah, I just heard about that.
Or about what?
You remember Marcus Walker?
She wouldn't remember, she just.
Oh, yeah, I know, that's why I wasn't sure. Like, when was he here?
I thought it was last year. Yeah, it was.
All right, what about this? What about this? This just makes sense. So you got a spherical raindrop. If it's falling through a layer of dry air, right? Where does evaporation occur on the raindrop? Well, from the surface of the drop, right? That's where the water is going to be pulled off. The water molecules are going to be pulled off by evaporation, right? Does that make sense? So it totally makes sense that the rate of evaporation is proportional to the surface area. When the drop has a big surface area, it's going to be more water is going to be evaporated per unit time than it would if it were small, right? Okay, so we're given that, right? So what does that mean? What's the volume of a sphere?
I had Thompson for
4/3
Thompson for
Pi r.
geometry, I'm not.
cube.
Yeah.
Okay.
Yes.
And surface area of a sphere is 4 pi. Anyone?
R squared.
Bueller? R squared, there you go. Okay. So we have V, we got S, right? Surface area, volume. And we want to show that this is true. Okay, we want to show that the radius is going to be decreasing at a constant rate. All right, so let's break this into a couple parts here. If they tell us that it evaporates at a rate proportional to its surface area, what's that mean? How do we write a proportionality? That's saying that V dot is proportional to S. So what's that mean?
No.
Or it's a
They changed the same, so that
They
means.
changed the same, but how do I write a proportionality as an equation?
V
That's, you
dot
can't do
over
algebra with a
something-
proportionality sign.
V dot over something equals S over X, I guess.
How about just like that,
Or that, actually.
right? V dot equals Ks, where K is just the constant of proportionality. We don't know what it is, right? But we do know that it's negative, don't we? Right, because V dot is negative. So let's say if K is positive, then we'd write it like that. Everybody agree? Okay, well, let's start up here with our parent equation. V equals 4/3 pi r cubed, and let's differentiate implicitly to relate V dot to R dot, right? What do we get? V dot equals, 3 times 4/3 is 4 pi r squared r dot, right? Okay, well, if we're told that V dot equals this, and we differentiate implicitly to find that V dot equals this, let's just put those together. Surface area is just 4 pi r squared, right? So look what we get from this. This is so cool. So we get then the equation. We get the equation. Oh my gosh.
Finish it in,
I'll save it. I thought I had it. We're so close.